When a substance changes its state, heat energy is involved. The energy is not to increase the temperature of the substance any further, but to separate the molecules from each other. This is known as specific latent heat and is different from specific heat capacity. Specific heat capacity is the energy required to change temperature of 1 kilogram by 1 degree Celsius, while specific latent heat is defined as the amount of heat required to change 1 kilogram of a substance from one state to another at constant temperature. So, in computation of specific heat capacity, there is a change in temperature, but in specific latent heat, there is no temperature change. Specific latent heat is the energy absorbed or given out when there is a change of state. For example, heat energy absorbed when a candle burns and solid wax melts. Two things are important. Firstly, specific latent heat is particular to state changes, meaning specific latent heat required to change ice to water is different to the specific latent heat to change water to steam. Secondly, there is no change in temperature during this change of state. Temperature remains constant. Temperature will only change once the change of state has completed. As mentioned, the heat energy during change of state is not to heat up the substance, hence no change in temperature. So where is the heat energy provided utilized? Does it simply vanish? And why is it called latent heat? The heat provided is used to break the bonds holding the molecules together. As this occurs at constant temperature, it is known as latent, meaning hidden. It is as if energy is disappearing, but in reality, it is used to break the bonds. If we heat a plastic fork to its boiling point, we get the following heating curve. Note the point B and C on the graph. The heat energy absorbed at the phase change is busy breaking the bonds between the individual plastic molecules. Once enough bonds have been broken, the fork will melt and become liquid plastic. After this point, if we keep heating, our temperature rise will be detected. The temperature will keep rising up until the next phase change, liquid to gas. At vaporization point, the temperature of the plastic will stop rising while it transitions to gaseous plastic. Once in the gas state, if we continue heating further, the gaseous plastic will rise in temperature. So breaking the bonds is why the temperature does not rise or fall when a substance undergoes state change. It takes different amount of energy to convert solid into a liquid, then to change a liquid into a gas. For example, it takes 7 times more energy for water to turn into steam than it does to melt ice to water. This means a substance can have two specific latent heat of fusion, which is the amount of heat energy absorbed or given out to convert 1 kilogram of solid to liquid or vice versa at constant temperature. Latent heat of vaporization, which is the amount of heat energy absorbed or given out to convert 1 kilogram of liquid to gas or vice versa at constant temperature. It is important to associate the correct specific latent heat to particular change of state. Now let's look at the maths. To calculate specific latent heat, we use this equation. E equals m multiplied L, where E is the energy supplied in joules, m is the mass in kilograms, and L is the specific latent heat measured in joules per kilogram. This formula can be rearranged. The units of specific latent heat are joules per kilogram. Let's do a practice problem. Remember, the specific latent heat of fusion is the energy required by water to change from solid to liquid. By writing the equation and substituting the values, we get 1.336 million joules. That is a lot of energy. We can convert this into kilojoules by dividing it by 1000. We get 1336 kilojoules. So in summary, specific latent heat is energy transferred to 1 kilogram of a substance to undergo change of state at constant temperature. It is of two types and we calculate it using this equation.